In turn-of-the-century Berlin, the mysteries of the Earth begin to intrigue another scientist. His name is Alfred Lothar Wegener. The son of a strict Protestant minister, he forsakes family tradition to become a professor of meteorology. One Christmas, he receives an atlas and begins to study a map of the Atlantic region.
Wegener later told this story himself. He said, I started looking at it, and it was really odd. He said, I'd always noticed, like everybody over the age of 12 has noticed, that Africa and South America fit together. He said, but this map had information from deep down in the Atlantic Ocean, and what it showed is that that match between South America and Africa goes all the way along the continental shelf, all the way down to the foot of Africa. Now, if this is the case, he said, he thought immediately and pointed it out to his office mate, this isn't just an accident of sea level that these things look alike. These things look alike because they're connected in some way.
Almost as a hobby, Wegener develops a theory that the continents, once connected, drifted apart over time. But he's an experimental meteorologist, not a geologist. So he spends the next 2 years in Greenland, gathering weather data. He also sets a European endurance record for ballooning, and even proposes marriage in a balloon to Elsa Koppen, the daughter of his mentor at Marburg University. But his theory of drifting continents keeps gnawing at him.
Wegener's original idea about continental drift was a momentary intuition. For it to get to be science, you have to make the idea real.
There were particular kinds of fossils found only in certain parts of the world, which Wegener found very puzzling to explain how they got where they were. This one comes from Brazil. See, it's got a long fish-eating skull, a very long swimming body, and legs that look quite like paddles. But the only other place in the world where these animals have been found was in South Africa. And here is a specimen belonging to the very same species that was found in western South Africa. See here, it's got the same long, thin skull, paddle-like limbs and big, thick ribs. How could this be? These two areas are nowadays 5,000 miles apart with the Atlantic Ocean between them. So what could be the explanation as to how they came to be in those two places?
Wegener then learns that certain geological formations occur in very unlikely places. Far above the Arctic Circle, in the frozen islands of Spitsbergen, there are large deposits of coal. But scientists believe that coal is formed in tropical climates. Wegener also discovers that great rock sheets, the result of ancient glaciers, stretch for miles across tropical South Africa.
You can have glaciers in tropical areas if you've got very high alpine-type mountains, but not great extensive ice sheets, and that's what the evidence seemed to show. And so Wegener argued that those continents couldn't have been there when those glaciations occurred and had to have been either further north or further south.
Putting all the clues together, Wegener suggests that the continents were once joined in a massive supercontinent called Pangaea, or All-Earth. The continents must have moved throughout geological time, drifting across the ocean floor. Before Wegener can publish, war breaks out in Europe. As a reserve officer in the German army, he's called up to fight on the Western Front. Injured early in the war, before the worst of the casualties, he continues to work out his theory while his wounds heal. The result is the origin of continents and oceans, his argument for continental drift. Geologists are not impressed.
Many of them said disparagingly this was a theory of the Earth proposed by a weatherman, who moved continents around the way clouds move, but the Earth is this big solid thing. Continents don't just get up and skate around like pats of hot butter on a skillet.
They were able to show that when there was a major earthquake, the Earth just rang like a bell. It pulsated, and long waves traveled around the surface of the Earth for hours and hours after a major earthquake. Now, existing physical theory said that anything that was strong enough or rigid enough to behave that way when there was an earthquake had to be far too strong to allow continents to move round at the surface.
The soft underbelly of Wegener's 1915 theory was the fact that he did not have a force by which to split Pangaea and then propel its pieces across the face of the globe to take up their positions as the modern continents.
Wegener didn't know what made the continents move, and frankly, I don't think he thought that was his problem. He felt that that was something that other people would have to work on.
In 1930, Alfred Wegener leads a new meteorological expedition to Greenland. He's undaunted by the negative reaction to his theory and has updated his book several times, writing in the 1929 edition that the odds of his theory being wrong are 1 in a million. The new expedition is plagued from the start. Bad weather pushes Wegener and his team over a month behind schedule as they rush to establish 3 bases before winter. On September 21st, Wegener sets out to resupply one of the bases. The temperature is minus 60 degrees. The 200-mile journey is planned for 20 days. It takes 40. Most of the supplies are lost in blizzards.
He said to his closest friend, this expedition is now nothing but a matter of life and death. And then the guy who lived for many years afterward and told this story often said, and then he did something that I'd never heard him do before. He talked about how he felt about the world. All I'd ever heard him do was sort of laugh and smoke and do science. And Wegener said, look, it doesn't matter what happens to individuals. He said, science is a social process. It happens on a time scale longer than a single human life. If I die, someone takes my place. You die, someone takes your place. What's important is to get it done.
After a day of rest, Wegener and his Eskimo guide try to return to their own base. They are never heard from again. Alfred Wegener died just after his 50th birthday. His idea of floating continents, still unproven, even ridiculed as a theory without a cause. The origins of earthquakes and volcanoes also remained a mystery. But in the years before World War II, other scientists become intrigued enough with Wegener's theory to take up his quest. For the next 30 years, they struggled to prove Wegener was right and to find the mechanism that could move continents. Only this time, they turn their attention away from the ground below to a place far more mysterious. This is where scientists seek the ultimate answer. The deep ocean floor, as alien as another planet. In the 1930s, geologists used World War I submarines to learn as much as they can about this new frontier. One of the pioneers is Harry Hammond Hess, a young graduate student fresh from Princeton. Hess had spent the late 1920s as a mineral prospector in Africa, even though he had failed his first mineralogy course and was told he had no future in geology. But despite that prediction, Hess eventually joins the Princeton faculty.
Harry was a totally remarkable character. Very quiet, little toothbrush moustache, great sense of humor. If you went into his office, you'd see his desk literally piled that high with papers, letters, minutes of this, minutes of that. I was with him one occasion, and he was looking for something of this, and he came across an unopened letter. He said, "Oh, I sent that letter. I should have sent that letter." And he opened it, and it was a letter to another graduate student 3 years earlier, offering him a place. He said, "Oh, I wondered why we never heard from him." This was Harry.
In 1932, Harry Hess joins a renowned Dutch geophysicist, Felix Venning Meines, who was surveying the Caribbean.
Venning Meines had borrowed a World War I surplus submarine from the U.S. Navy for this purpose. Well, these submarines were not the QE-2. They were small, cramped, not very competent things, and dangerous. Something went wrong and the submarine went way below its designed maximum depth. And only drastic action by the captain actually saved their lives.
Hess and Venning Meines can detect minute variations in the mass or density of seafloor crust by measuring the force of gravity with a specially created device. The delicate pendulums are slightly more attracted by denser rocks, rocks exerting a greater gravitational pull. It's so sensitive, it can only be operated in deep, still water, far beneath the turbulent surface of the sea. The measurements reveal something surprising. Large areas along the margins of continents, where the seafloor seems much less dense than expected.
It was as if pieces of the ocean floor were missing, as if the rocks just weren't even there. And this meant that there were forces actively disturbing the crust. And if that were the case, maybe those forces were also moving the crust.
Harry Hess is at Princeton in December 1941, when Pearl Harbor is attacked. An officer in the Naval Reserve, he travels to New York City the next day to report for active duty. By 1943, he's the captain of a transport ship in the Pacific. It's equipped with sounding devices, and Hess uses every opportunity to take depth measurements of the ocean floor.
He ended up to the war taking in Marines onto some of those horrific landings on the Western Pacific Islands. Throughout the war, he ran his echo sounder, and he came back with an enormous volume of soundings on the floor of the Pacific. It showed for the first time, very clearly delineated, the deep ocean trenches around the western margin of the Pacific. Very curious features.
Then, in the early 1960s, another piece of the puzzle. Core samples of the ocean floor are taken in the middle of the Atlantic. Analysis of the rock reveals that the Earth's crust gets progressively older on either side of an undersea mountain range called the Mid-Atlantic Ridge.
The Mid-Atlantic Ridge has been known for a long time. It caused a lot of trouble when people were laying telegraph cables in the 19th century to have a big mountain range at the floor of the Atlantic, so people knew that it was there.
Researchers find that the Mid-Atlantic Ridge is not only younger than surrounding ocean floor, but it's made of volcanic material.
The Mid-Atlantic Ridge seems to be a pile of cooled lava on top of a fissure or an opening in the Earth's crust through which hot material is constantly coming up from the Earth's interior.
Hess suggests that the mid-ocean ridge is the site at which the continents are breaking apart. The mid-ocean ridge is formed when molten rock rises from inside the Earth and then pushes the crust apart.
Hess suggests that the reason the ocean floor is young at mid-ocean ridges is that that's where new crust is being created.
And so Hess argued that, in fact, not only was new crust in the oceans formed at the surface, but it traveled along horizontally and then dipped down back into the interior of the Earth again, a process called subduction. And this was the true significance of the ocean trenches, which he'd spent so much of his earlier years working on.
Hess writes this idea up in an article. He calls this paper an essay in geopoetry because, of course, he knows that Wegener was severely criticized 30 years before for an idea that was not that different. So by calling it geopoetry, he's taking a kind of moderate stance. Don't get too upset, don't take this too seriously, but I think it's clear that he believes the theory is true.
Hess's theory suggests that the sea floor moves due to circulating currents deep inside the Earth. The material beneath the crust is kept hot by the constant decay of radioactive elements, causing convection currents that move the ocean floor along. New crust is created at mid-ocean ridges and destroyed at deep ocean trenches, Hess suggests. A never-ending conveyor belt, moving at a snail's pace through the ages. His paper is greeted skeptically by the geological community. But at Cambridge University in 1963, geophysicists Fred Vine and Drummond Matthews uncover new evidence that supports Hess's theory. Evidence based on rock magnetism.
They, with a brilliant piece of lateral thinking, looked at the ocean floor south of Iceland, but in other places as well. And south of Iceland, you've got part of the mid-ocean ridge in the Atlantic. And there was a feature of the ridge which had been known for a long time, but no one had understood. And that was that there were curious magnetic stripes on the ocean floor parallel to the ridge crest.
Throughout geological history, there had been times when the Earth's magnetic field had reversed, meaning the North Pole had become the South Pole and the South Pole had become the North Pole. Since rocks are like little magnets, they would point in the direction of the prevailing magnetic field. And then, as the crust split apart, if there had been a magnetic reversal in the meanwhile, this next set of rocks would point in the opposite direction.
And they were able to show that the width of these magnetic stripes was proportional to the known durations of these normal and reversed epochs in geological history. Furthermore, the stripes were generally symmetrical on either side of the ocean ridge, as Harry Hess's seafloor spreading idea would have suggested.
It's nuclear testing during the Cold War that provides the clinching evidence. In an effort to monitor the tests of other countries, the United States and Britain set up a worldwide network of seismometers, which also detect earthquakes. Now, geologists can map the locations of earthquakes with unprecedented accuracy. And soon, a pattern emerges with stunning clarity.
The earthquakes occur in exceedingly narrow bands, and these red spots are shallow earthquakes, and you can see them following the crest of the mid-Atlantic ridge all the way down. If we look over here in the Pacific, you can see that these necklaces of oceanic islands and the deep ocean trenches that lie against them are associated with earthquakes too.
You put this all together, and what you get is plate tectonics. The idea that the Earth's crust can be broken up into large pieces or plates that consist of both continents and also pieces of oceanic crust moving together over the face of the Earth.
The movement of the plates is only a few centimeters a year. But that's enough to reshape the Earth, build mountains, trigger earthquakes, and create volcanoes. Volcanoes erupt where the crust splits apart or where it subducts, and molten rock is forced up from below. Mountains, like the Himalayas, form where plates carrying continents collide, crumpling up the land over millions of years. And earthquakes occur along the boundaries of tectonic plates, like the San Andreas Fault. In 1906, the Earth had suddenly snapped along the fault line, releasing pressure that had been building up for years, caused by the slow, steady movement of the tectonic plates. Our planet is not merely a static platform for life. Although it appears placid from outer space, the Earth is dynamic, violent, unpredictable, constantly reshaping itself, much as Alfred Wegener had suggested 50 years earlier.